Tarzan and Tarzana are brawny ape people. I don't know what that means. Were they raised by apes? Are they like a mutant kind of thing? And what does brawny mean? I guess, yeah, it's like a type of paper towel, right, kind of thing, and but I don't know, it's just weird. Anyways, they're brawny ape people. They decide to have a race across the river. Both are excellent swimmers and have the same ability. In other words, they can both swim at the same speed. Tarzan swims straight across, landing on shore directly across from where he started. Tarzana jumps in and points herself across the river, but ends up farther downstream when she reaches the other side. The two are pictured in 324. So the question is, who finished first? So, looking at that picture there, Tarzan is the one on the left. She swims sort of against the current and ends up going straight across. Tarzan, he swims straight across because of the current, ends up downstream. Which one do you think finishes first? Okay, you kind of wasn't. Yeah, exactly. Who do you think finishes first? Or is it the same?
First picture.
Okay, because the result is shorter, Joey says. Okay, well, we're going to get the answer. I just wanted you to make a prediction. Then there was Cheetah, faithful brawny ape pet. Exactly. Is he an ape? Is he a cheetah? Does he necessarily need to be brawny just because his family is brawny? Is he somehow a mutant ape? Or is he just an ape?
Maybe he's the son of Tarzan.
It says he's his pet, not child, so. But maybe, right? Maybe in some twisted biological senses. It's all very confusing. Makes me wonder who's writing this thing. Okay, he chose to swim across the river by the time when the floods were raging and the river flowed at 5 times the velocity it did when Tarzan and Tarzana swam. Cheetah 2 is a good swimmer and has the same ability as Tarzan and Tarzana. Did Cheetah finish the crossing in a short time? Now, as you can see, the far right picture, Cheetah went considerably farther. But did it take him any longer time? What is your gut telling you? Is your gut telling you that this might be one of those situations where I'm not really sure what's going on? Yeah. Okay, so we're going to have to do some math. Relative motion. Trying to answer the proposed problem, we need to define what relative motion is. Suppose you're traveling in a car and are being observed by a highway patrolman sitting by the side of the road as shown in figure 325, which of course is on the next page because that's great textbook ready. The patrolman, you see them over there on the next page? Okay. The patrolman will measure your velocity relative to his position. In this case, the patrolman is not moving. Let's assume the velocity he measures is 140 kilometers an hour. Your velocity is said to be 140 kilometers an hour east, measured relative to the ground. Okay, so you flip the page over, you see the fuzz standing on the side of the road there. Got his radar gun out, you're doing 140. You're not very smart. Clearly you can see a police car on the side of the road. I would suggest you slow down. Okay, but your speed is 140 kilometers an hour relative to the ground. Now suppose you pass the patrol car with a velocity of 140 kilometers an hour while it is moving with a velocity of 100 in the same direction. Also a bad idea. You just passed a cop car doing 140, he's doing 100. You're going to get tased. Bad idea. This time though, the velocity measured is 40 kilometers an hour relative to the patrol car. While the patrol car has a velocity of 0 in its own reference frame, its 100 km an hour velocity must be measured relative to the ground as in figure 325b. Notice that your velocity is the same, but the two measurements done by the patrolman are different. The bottom line is that the velocity value is measured relative to some reference frame, and we did talk about that in grade 11. In everyday use, we are accustomed to using the ground as a stationary reference frame. This frame is implied in most problem situations. If it doesn't say so, you can assume a stationary ground. Okay, so looking at the picture there, part B, the patrolman, the police car would measure your velocity 40 relative to him, but he's already going at 100, or he's already going at 100, so your overall speed is 140. Now we apply this knowledge to swim in the river. If Tarzan floats with the current, it will appear to her that she is not moving relative to the y. To actually measure her velocity, someone must stand on shore relative to ground and watch her go by. In fact, to measure the river's velocity, we must also measure it relative to the shore. In order to keep these velocities distinct, we use a series of very confusing subscripts. VOG is the velocity of the person or object relative to the ground. VMG is the velocity of the medium the person or object is in relative to the ground. VOM, blah, 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 blah. Someone probably wrote something in the margin of your book. No?
Yes.
There's a few that still have books that don't have that written in? Wow, okay, so let's do this then. Those of you that still have those, let's do this. Would be why I had that blank page. Okay, so VOG, velocity of the person or object relative to the ground. I'm going to just call that VR. It's the resultant. It's what you see if you're just a regular person standing on the ground. VR, or just resultant. It's the same as VOG. Is that what you guys have in yours? The ones that are written in? VR? Okay. VMG, velocity of the medium. Now we're not talking small, medium, large here. We're talking about the medium is what it's in. So quite often in these situations we're either in a river where there's current or we're in the air where there's wind. So I would say something like VC or VW. It's the current or the wind. VC, yes, velocity of current velocity. I tend to just call it C. Too many subscripts. But I'm trying to sort of give you an idea of what they're talking about here. And the last one, VOM, is the object relative to the medium. So what we're talking about there is the velocity of the plane, or the velocity of the boat, or the velocity of Tarzan, or the velocity of Cheetah, faithful brawny ape pet. I'll just say actual plane or boat speed. Okay? It's what the speedometer shows inside the plane or the boat. Have I simplified what the book has done? I guess we'll see. The relationship between the three quantities is VOG is equal to VOM plus VMG. Once again, very confusing. I like to just say the resultant is plane plus wind. Right? And you can substitute that if you happen to be talking about a boat plus current. In our particular situation here, the resultant is Tarzan plus the current. Right? They're trying to make a generalization by using these fancy VOG, VMG stuff, and it just confuses everything. Okay, let's go right to example 7. You guys have this, right? Okay, so we're going to start really simple. Relative motion, one dimension. In one dimension, the river problem has 3 possible cases shown in figure 326. When the river flows, its velocity is 1 meter per second east. Tarzana can swim at 2 meters per second in still water. So in case 1, Tarzana swims in a dammed up river. That's referred to as a lake. No current. Case 2, she swims with the current because the dam broke. Case 3, she swims against the current. Yeah, so they're pretty straightforward here, right? So with no current, let me just see here. Okay, so we've got here case 1. Resultant is, I'm all out of Kleenex, Daniel. Yeah, sorry, man. I just gave you one. Okay, so when there's no current, it's obviously pretty easy, right? It's just going to be 2 meters per second east plus 0. What's the resultant? 2 meters per second east, of course. Right? And they show that there, and they make it nice and confusing. Case number 2, this time swimming with the current. The resultant is Tarzan plus the current, so we're talking 2 meters per second east plus, is it 1 meter per second east? No components needed, it's 3 meters per second east. Right? And against the current, no big stretch here. 2 meters per second east minus 1 meter per second. Now, how should I write this maybe? She's actually swimming west, right? The current doesn't change but should I put plus, do you think? Probably, right? I think that's probably more appropriate. And I think we can all agree that that's going to be minus 2 plus 1, or simply either minus 1 meter per second or 1 meter per second west. Either of those is fine. Let's go down to example 8. Here's where we get into 2 dimensions. Tarzan swims at 2 meters per second. The current is 1 meter per second east, and Tarzan is seen to swim directly across. What the heck does that mean? He's seen to swim directly across. Okay? His resultant is directly north. That's right. Someone standing on the shore sees him going straight across. The current is 1 meter per second east. Now, there's the current there, and Tarzan is, so in other words, he heads off like that, right? Now I think that's actually, I just realized that. That's different from the original setup, isn't it? No, that's not. Tarzan swims straight across. Okay, so what is the resultant then? So in this case here, are we doing vector subtraction here? Sort of, kind of, but it's one of those kind of gray area ones. We can do it right from Pythagoras because it's that right triangle. So t squared is equal to c squared plus r squared. Oddly enough, the result is not the hypotenuse. Do we know Tarzan's speed? Yes, we do. It's t squared. The current speed is 1. We are solving for a result. R is equal to 1.7. And of course we need the angle. Now I use tangent, so that's going to be opposite 1 over hypotenuse 1.7. Easy enough to make a mistake here. And you get 30 degrees. So in other words, Tarzan knows the river's going to push him downstream, and he's done this swim before. He knows that if he heads off at an angle of north 30 west, he will end up doing what? Going straight across. Could we do this via vector subtraction? Resultant is Tarzan plus current, not t squared. Notice that whenever I do Pythagoras, I'll never put a vector sign on here. These ones I tend to, sometimes I forget, but this is different, right? Could I do it by vector subtraction? Because I'm really trying to figure out here, well, no, I'm trying to do resultant, aren't I? So it's not vector subtraction, is it? Because I know t. You see, this is one of those confusing ones because you know t, but what don't you know about t? We don't know the angle. It's one of those stupid, crazy ones that books never seem to be able to get right, is that they try to tell you it's vector subtraction, but they're not really giving you enough. So, yeah. Tricky. What about Tarzan? What does she do? She's the one that goes straight across and ends up doing what? Floating downstream, right? Her situation looks like this. She swims at 2. Current is 1. She is seen to direct her body directly across. In other words, she tries to go straight across and ends up going down like that. Which one are we trying to solve for here? We're solving for r. This time the r is the hypotenuse. R squared is equal to t squared plus c squared. 2 squared plus 1 squared. This time it's the square root of 5. Her resultant is 2.2. Is her angle going to be 30 as well? Your gut tells you, oh, maybe it will be, right? No, Joey, why not? Okay. Tangent is opposite over adjacent, so 1 over, my adjacent is 2. Here we had 1 over 1.7. She goes downstream at north 27 east. Slightly different. We still haven't answered the question, who gets across faster? Have we? What do you think? Which one is actually traveling at a faster speed? To an observer in a helicopter above the river, which one is seen to be swimming faster? Tarzan or Tarzana? 0.2 compared to 1.7. She's swimming faster. Her rate of speed is faster. But what? She travels farther, doesn't she? So we still don't know. We'll find out. Does it say here? I always forget. They want us to deal with cheetah first. Faithful briny 8-pet. Cheetah swims at 2 meters per second. The current is 5. Cheetah swims like Tarzana, pointing directly north and ends up going downstream. So same idea here. Cheetah, current, big C, little c. R squared is going to be equal to 2 squared plus 5 squared. Cheetah's resultant velocity is 5.4. And of course his angle is considerably more. Opposite over adjacent. Opposite is current, which is 5 over adjacent, which is 2. Big angle. North 68 east. Okay. On the top of 101 it says, find me the time to cross. I'm going to answer the question now. So who finishes first in the race? Well, to find out, we need to look at the 3 vector diagrams which are shown together in figure 335, which is right there. The equation v equals d over t, rearranged to find time, becomes t equals d over v. We now need to find out which v to use. If you look at the diagrams, the velocity vector that points in the direction of the desired motion, north in our case, is the appropriate choice. The other vectors involve the motion of the current, which does nothing to help anyone cross to the other side. Tarzan swims at 1.7 in the north direction. Notice that for Tarzana and Cheetah, the velocity direction north is 2, right? This velocity here is 2. This one here is 2, but in Tarzan's case, his north direction is a velocity of 1.7. That's all that matters, is how long it takes to get across. Okay? In this particular situation. Notice that for Tarzan and Cheetah, the velocity direction north is 2. Thus, Tarzan finishes last, with Tarzana and Cheetah tied at first. The lesson of this story is that if you wish to cross the river quickly, then direct all of your energies to do so. Tarzan used up some of his velocity in fighting the current in order to end up in a position directly across the where he started. So if you're being chased by apes, and you're a faithful briny 8-pack, just swim across the river and let the stream take you downstream. It don't matter, right? You'll get there fast. Don't try to swim against the river. You're burning up energy, burning up velocity going that way. Okay, let's look at example number 9 here. Airplanes. This is the last one. Is this the last one on your page too? For airplanes and flight paths, the method of approaching the problem is the same as for our general surface. The velocity of the plane relative to the ground is the velocity that we see. It's the combination of the plane's capability, called the velocity of the plane relative to the air, and the velocity of the air relative to the ground. These two velocities continually combine throughout the flight to produce the final velocity you see. In other words, the plane speed plus the wind speed give you the overall result. Let's just cut right to the chase and make it simple. Oh yeah, this is another one of those stupid ones. The pilot with a heading of north 30 east at an airspeed of 400 kilometers an hour flies into a wind coming from the north at 110. As soon as you have a plane in a wind, be very, very, very careful at reading which direction the wind is going. Because some places will say from the north, and others will say towards the north. Right? So read very carefully. What is the plane's velocity relative to the ground, and how long would it take to complete a journey of 1,000 kilometers at north 30 east? Let's draw a picture, shall we? Pilot with a heading of north 30 east. North 30 east. And an airspeed of 400. So this is my plane, and I'm headed out at 30 degrees east of north. Flies into a wind coming from the north. From the north, we'll point to the south at 110. Let me move my... Oh, can't do that. My wind is like this, right? What is the plane's velocity relative to the ground? To someone on the ground, how long would it, what is their velocity? So in other words, we're solving for result once more. How long would it take to complete a journey of 1,000 kilometers at north 30 east? Is the plane going to end up going north 30 east? That's my result in there. No. Textbook error, once again. My guess is that the original author had the correct angle in there, and then someone in editing changed it because they thought that wasn't right, and they turned out to make it more confusing for students. Don't become a textbook editor. Or if you are, be a smarter one. Okay, so is this vector subtraction or is it addition? It's addition, right? Because we're solving for a result. Resultant is plane plus wind. It's a non-right triangle, so how are we going to have to do it? You could use sine law and cosine law if you want, but remember how I showed you the other day with components, how simple that was? Let's do by components, okay? Okay, so there's sort of our basic setup. I would strongly recommend let's redraw. Plane X, plane Y. Oh, by the way, I marked the vector ones last night. The one mistake that I saw that was the most common was people, when they went north 30 east, like for example here, I drew it wrong, didn't I? Because it's north 30 east. So if I put 30 in here, is that north 30 east? That's east 30 north, isn't it? And that's the mistake that I saw, and I'll give those back to you today. What should that number be in there if I'm going to draw it like that? It should be 60, right? So I can either change that to 60, or maybe I should redraw it north 30 east. If you see north 30 east, then draw north first, and then east. And put 30 there. PX, PY. Is everybody with me still? I know it's a hot day. It's a real long day, isn't it? Good question. Jake wants to know if we have to change it into meters per second. Does it ask for the answer in meters per second? Is time measured in seconds anywhere in the... Only if you have to make units match, but everything's in kilometers an hour, Jake, so let's just leave it like that. Okay, or did you do that already? Yeah. I actually noticed that students did that before. They change it to meters per second, they do all the work, and then they change it back at the end. So you don't have to do it. Okay, so PX is going to be, X, is it opposite or is it adjacent? It's opposite, so it's going to be sine. So PX is going to be 400 sine 30. or 200. It's to the right, so it can remain positive. Py is then the opposite. 400 cos 30. Py is up, so it can be positive. 346. Now let's add the wind in. Wind was straight south, wasn't it? I'll put it in red just to keep it consistent. At 110. So wind x. What's the wind x? 0. Wind y. 110?
Negative.
Y negative. So it's down. Very good. Add them. Rx is equal to 200 plus 0, or 200. Ry is going to be 346 minus 110, which is 236. Here's the part where I strongly suggested that you draw a picture. Some of you didn't heed my advice on the little quiz that I took in yesterday. So it's going to be 200 this way, 236 that way, giving me an overall result of, let's do Pythagoras, 200 squared plus 236 squared, 309.3 kilometers per hour. And of course we need an angle. Opposite over adjacent. Opposite is the y, so 236. The adjacent is the x, 200. Degrees, or north, no, hang on, it's not going to be 40. What is it? It's not 40. I wrote 40 down because that's what was on my page, but I neglected to watch my page when I was drawing this diagram, and I drew the y first and then the x, and so I have this backwards. So I think if you go 236 over 200, you should get 50. Did anyone do it yet? 50, Jason? Am I right? Okay, so yeah. So it's east. Okay. I had it drawn the other way here, but I didn't look at that, but then I looked at the answer. It happens. Concussion. It's the ace in the hole. Gets me at anything. That's just really an example of vector addition, isn't it? Right? With word problems, instead of just sort of add this vector to that vector, right? You guys want more vector subtraction, don't you? Because you're worried. Yes, I know, I can tell. Do you want just plain Jane, take these two vectors and subtract them?
Yes.
Yeah, we should talk first. New questions and all of that.
Okay. Here's what I've got. Here I see that on page 103, number 2, and 116, number 35, 36, 41, 42, and 43. There's also that sheet that I just handed out that I'm short a few. This one, I guarantee you, I wrote these myself. Actually, these are questions that I wrote for a math textbook, and then I just stole them for myself, which I think is illegal, actually. They have their subtraction question on the bottom. I guarantee you I wrote these properly. They are true vector subtraction questions. I spent a lot of time making them just right. Okay, so there are vector subtraction questions there. There are answers. There are solutions on that scan code. I will see if I can cook up a few, take these two vectors and subtract the kind of questions for you, maybe by the end of this period. Okay, I'll go make some more of these.
The answers are only 1 to 5, but it's actually 1 to 7.
That I don't know.
Well, you made it, so.
Yeah.
Having to do the answer.
I don't know. Scan it. See if I've got them elsewhere.
I don't know, I can get it.
Yeah.